I'm Moses. Thanks for joining me on this presentation. Today I'm going to be presenting forecasting New York noise complaints with Bayes. Just wanted to say a little bit about me. Professionally, I work as a data engineer, and as you probably already know, I'm interested in Bayesian modeling. Specifically, I'm interested in how Bayesian modeling can be applied to stress in the real world as it relates to 311 data. See? Before I begin, I want to share a couple of resources. I have them at the top of the chat. And the first resource is just the GitHub repo that I've done my analysis. You can look in the notebooks folder to see all the analysis for this presentation. Secondly, the second link is just a zip file. And the zip file contains some maps that will be used later in the presentation if you want to interact and explore some of the data results. So the key takeaways that I want you to learn from this presentation is, first of all, just learn about what is Bayesian thinking. I want you to learn about understanding how you can build models using Bayes. And the final thing is, I want you to basically, when you ever have a project in the future, considering Bayes as a way to conduct analysis and develop insights from the data project that you may have. The data sets that I use for this presentation, first of all, is New York 311 data. It's filtered by noise complaints. I broke it down into using two different geographic data units. The first is the neighborhood tabulation areas, and they're broken down to populations of 15,000. And the second is the census public use microdata areas, which is also known as PUMA, and they're focused in groups of 100,000. Some of you may have the question, why didn't I use zip codes? And honestly, when I first started about doing a data analysis, I thought about using zip codes as my default geographic analysis on data. But this may seem obvious as you start to learn about zip codes that they're really intended for postal codes. And these geographic data sources are intended for statistical analysis. And that's why I chose those. When I started this analysis, I was focused on just 311 noise complaints in general, but then I quickly realized that I needed to limit the scope. So for this presentation, I focused on the summers between the months between June through August, and I focused on years of 2021 through 2025. 2021 through 2024, I used for training data, meaning that I used to actually build the model. And 2025 is like the unknown year. And so are the test data. And as I looked through the 311 noise data, I just discovered there are many different categories, ranging from what we already know, which is clubbing, things like that, to I've seen like noise complaints due to boats. And so I arranged them down into 5 categories. Animal, construction, mechanical equipment is more so like cars, things like that, social party, and others that contain everything else. Before we begin, just have a kind of an exploratory analysis. There are many different questions to ask about the data and many different ways to explore the data, but I tried to get into the fundamentals. And you can see like the minimum maximum noise complaints here. I just got to resize the screen because it's a little smaller. You can see the minimum maximum, the average noise complaints here. You can see that New York can get really loud at some times and New York can get quiet at little times. And also I try to look at just how does, in terms of the categories that we have, how does in day and night, how do people complain? And you can notice that, and it may seem obvious, but it confirms that most people complain about noise due to parties, things like that. And especially at night as opposed to the day. So this is one of the most important slides that I want to introduce. And I know it can be difficult to understand, but I try to, and this is an abstraction of what the Bayes model actually is. And so if you have any questions and just misunderstandings, I really want you to understand this. And the way to understand Bayesian analysis. So for me, I think about it as an example. When I was younger, I liked eating a lot of unhealthy food, pizza, soda, hamburgers. But my intention was I wanted to be healthy. And so prior experiences, my goal is to eat healthy. And I'm thinking eating pizza, hamburger, and I'm just naive to eating pizza, hamburger, and hot dogs is maybe healthy. But then most recently, I read a book about eating healthy. And so the likelihood is that data, that basically like that book is that data. And the book taught me that I have to eat my greens, I have to eat my beans and things like that. And so my prior experience and my prior knowledge is not aligned with the likelihood. So my prior knowledge is probably like a 0.2 at terms of eating healthy, or a 0.1 or 0. And then the knowledge basically behind those things go to the posterior. And the posterior just basically updates my understanding about eating healthy. And so now eat more vegetables. And so I update my posterior, but then it goes back to my prior experience. And that continual knowledge cycle it occurs over and over again. Standardization may be a difficult, it basically, and from a mathematical perspective, it just basically normalizes everything. But the Bayesian thinking is this process of you having some type of starting knowledge about something. And then you basically, the likelihood is like that score that's trying to match your knowledge with the actual data. And then you have an outcome and you repeat that process over and over again. Why use a Bayesian model for noise complaints? And so one of the reasons I chose noise complaints is because I remember last year when I was watching the New York Mayor City debate, there was a question about 311 complaints in New York. And the top complaints in New York was about noise complaints. And I thought, might as well explore that. And one thing about noise complaints is that, as you can imagine, that different neighborhoods have different number of noise complaints. Some neighborhoods may have more, other neighborhoods have less. And there's uncertainty on different days. Some days may have more noise complaints, and within neighborhoods, some days neighborhoods have more complaints, and other neighborhoods have less. And so the other thing with Bayesian model, unlike machine learning, and I know machine learning is more popular, is that machine learning is like a black box. You don't really quite know how it works, but you just basically put something in there, throw the data in there, it does its computing, and then out becomes a result. And sometimes that result is perfect for the past, but when you try to fit that result to the future, it just doesn't work. It's just trying to focus on the past. It's trying to focus on the ideal case from the past. The way Bayesian model works is that you structure the model based on how you think the data is structured. And so it's transparent in that way, and you're dealing with it being probabilistic. And so basically you're dealing with a variety of the models. So the outcome is not fitting the perfect ideal. You're automatically including that in because it's dealing with that probabilistic. So there are a couple of fundamental questions that we want to answer when we're looking at the noise complaints. First of all, we want to look at how the noise complaints vary across neighborhoods. Secondly, we want to look at whether the noise complaints are high and low. And also, we want to look at, can we use the models to basically predict and also capture the variability among the noise complaints? So one main concept that I want to get across with modeling is that at a high level, we can structure the model based on the mean or the average. And there are different ways that we can structure the models around the mean. The first way is called the fully pooled way. And what that means is that we just have one mean that's across all the noise complaints. The second is unpooled. And that's where we're going to start to involve the geographic data, and we're going to focus on the NTA data. And so each neighborhood has its own individual mean. The third model we're going to look at is partially pooled. And that basically says that we have the NTA data, but we're going to basically look at relationships between data using the relationships between different neighborhoods using the PUMA data, because the PUMA data covers 100,000, whereas the NTA covers about 1,500. And so the reason we can do that is because we have this kind of common mean to the PUMA, but we have individual variability among these different neighborhoods. So here's the first model. This is structure the first model. And so we have this normal distribution, this log normal distribution. And so what I would say in building Bayes, what we're doing is we're working with distributions as if they're like Lego blocks. And we're constructing these distributions. And there are distributions that are compatible with the input, and they produce a certain output. And so in our case, we're using the normal distribution attached to a log because we assume that noise complaints are positive. With our likelihood, like I was saying before, that we have the data, And we're attaching it to a posterior distribution because posterior distributions work well with counts because we're looking at how many complaints per day. And once we use this, we have an output, which is the posterior distribution. And so everything has a common mean. Just right up here in this little graphic that shows the fully pooled. And as you can see the results here, as we looked at the exploratory data analysis, the social party was the most popular, most common complaints. And I would say that the scale is a little different, even though the plots are the same size, so just don't get thrown off of that. But you'll see that the social party has on Sunday, 3,000 complaints at the maximum, and on Wednesday, 1,000. So the Wednesday is the quietest day for social party. The thing that kind of surprised me with this data is that construction falls a little lower. I thought it was going to be a little higher, but yeah, more people complain about mechanical equipment here. And so you can see how noise complaints vary not just by category, but also by day. With the first model, we started with a simple model, but there's opportunities for us to improve it. And one of the main opportunity is just with geographic data. So let's see if it's loading. Okay. So we have the unpooled model, which is model 2. And so we're going to basically use the exponential distribution and apply it to the posterior with the likelihood, the post data with the data for the likelihood. And so the main thing that really changed here is that we're applying the NTA data here. And just a side note, if you look into, like I said, the GitHub repo, you can actually, in the notebooks, you can actually see the models, and they were all programmed using the Python library PYMC. And so right here, I have the quietest neighborhoods and some of the neighborhoods you may recognize. But one thing that I want to point out is if you see the observed data fits within the variability of the model mean. And this is at the quietest neighborhoods in New York. In the mid-range New York, it's still the same. The noise complaints fit in with the variability of the model. It's still a little off of the mean, but that's fine, but it fits in with the variability. So the one thing I want to point out here is that you can see as we get to the noisiest results, and it's a little scaled out, so do you see the confidence level kind of a little smaller? But that some of the noise complaint, the actually observed mean is a little outside of the model mean. So that means that there is some opportunity for improvement. Some of the problems with this model is that there are some neighborhoods that have a lot of data, a lot of noise complaints, and there are some neighborhoods that have a little noise complaints. For the neighborhoods that have a little noise complaints, it's really difficult to find a mean and a confidence. And so that means there's wider variety around that data. And for the neighborhoods that have a lot of noise complaints, you can actually easier find a mean. And so that's one of the things. And so and the other thing is that there's no sharing across neighborhoods. There could be some relationships with noise complaints across different neighborhoods. And so that's when we get to the next model, because what we want to do is we want to find the patterns that improve the mean by finding those patterns between noise complaints that are shared across neighborhoods.
Moses, sorry to interrupt, but there are quite a few questions that have been building up on the Zoom.
So what questions?
The first question is, did you see any unusual patterns in the summer of 2021 that might be associated with the COVID shutdown?
Actually, I didn't look that detailed into the data, to be honest. I did a high level, but that's actually really good questions. There are many ways you can view the data, obviously, but I should look into that, obviously. Yeah.
Okay. And then Catherine asked, does Bayesian thinking require iteration?
Yes. That's what Bayesian thinking is about. So a way to think about another example that I think about when I think about Bayesian thinking. So there's two general perspectives in statistics that I explained, and one perspective is a frequentist perspective. And say, for example, you're flipping a coin. The frequentist perspective is that we all know that if you flip a coin, it's always going to be 0.50%. And the reason we know that is because if you flip a coin a million times, it's going to land up with 50%. The Bayesian thinking model is that if you flip a coin, say, for example, the first time it lands heads, for example, and you say, oh, it's 100%, but that's all you think is 100%. But then you flip the coin the second time, lands the heads again, so you're just consistent, 100%. The third time, you get a tail, and so it's 2 out of 3, so it's 0.667. And so you think, okay, it's 67%, it's not 50%. And so what's happening is every time that the event occurs, you're basically updating your prior knowledge. And so it is an iterative effect. And so it's thinking about it as if you're iterating. You're starting with your current knowledge, your current experience, or whatever. You learn from it, and then you update. Yeah, it's continually cycled.
Okay, there's still a couple more questions. Adam asked why you're doing a log distribution with pooled and exponential with unpooled.
I chose the log distribution because it's a way of standardizing, as well as it's the way because the noise complaints are positive. I just chose it that way, and I wanted, yeah, the normal. Let's see, what's the second question?
With the next question, it was just confirming that for your slide on the quietest neighborhood, they were just confirming it's not necessarily the quietest neighborhood, just the neighborhood with the fewest noise complaints.
Exactly. Got it. Yeah, that's a better clarification as opposed to the quietest neighborhood says fewest complaint.
Okay. And then Sherry asks, please define social party. There's no quote problem, formerly complaint type category called social party in the 311 service request dataset.
So I aggregated it, and so I would say look at the notebook and look at the helpers.py file. And so I don't really have it's like I said before, the noise complaints vary, and so I basically took keywords off of the noise complaints and I just aggregated it wherever category it fell in.
Okay, got it. And then the next question was from Maggie. They asked do you have any DB data?
No, so if you look at the notebook and you look at the file called get that data, or you'll see that I download the data directly from 311 as well as Census, as well as the New York Data City site. And also I made it, what do you call it? I made it a script, so you could just basically run the script, but you could just run it directly from the notebook. So no, there's no database that I'm getting it from a database, but I'm not directly using a database for it on my DOM.
Okay. Yeah, I think those should be all of the questions that were directed at you. Yeah, sorry to interrupt again, but thank you.
No, it's fine. It's fine. So one of the key points that I want to share is that with sharing noise complaints across different neighborhoods, what you're going to do is you're going to basically move the actual. If you had a neighborhood that has a small amount of noise complaints, you're basically going to increase the confidence, and you're going to move we're going to move to the actual mean as opposed to the mean that it thinks it has, because you're sharing across different neighborhoods. And with the assumption that there is some relationships between neighborhoods in terms of noise complaints. And that's what you call the concept called shrinking. And that's what we're doing for the next model. So in the next model, what we're doing is we're basically have the NTA data, which is like each neighborhood by neighborhood. And then we're grouping that by Puma data. And what that's allowing us to do is to find relationships between the different neighborhoods, so that for neighborhoods that have less complaints, we're increasing the confidence level, and we're moving the actual mean that was predicted in the previous model closer to the actual mean. And it may not necessarily be the actual mean, but we're actually moving it closer because we're seeing the inter-neighborhood relationships between the data. So one method that we use to compare different models is called the PSIS-LLO method. And we can see here we have model 2 and we have model 3. And the red indicates how off or less accurate the model 2 is compared to model 3. But also you see this little line up here that basically says how confident it is. So you can see that model 3 is a little more accurate than model 2, but model 2 is not completely confident, and not as completely confident that it's off. So it is a little more accurate, but it's not completely accurate. This chart here shows you comparing model 2 to model 3, and also shows the shrinkage that is occurring. And you can see that the mean here for model 3 is actually moving closer for all the neighborhoods. It's moving closer to the actual mean, so it's moving to the right, but it's not necessarily, like I said before, it may not necessarily be the actual mean. It's just including the inter-neighborhood relationships helps improve the actual output of the model. So one thing I want to show is the actual, we'll call it map of New York City noise complaint. Let me get that loaded in my browser. And that's from the downloaded file. It should be, let me get that. I just have a couple of things loaded in my browser. So this is New York City here. And you should have it from the downloaded file that I shared, the zip file. If you open that, you can see the map. And you can see like right here, and the lighter colors are the neighborhoods that have higher noise complaints, and the darker colors are the neighborhoods that have lower. And you can actually animate it, and it's not the actual day, but I just put 5 days a week here. You can actually animate it and see the noise complaints throughout the week. And a couple observations with this data is that you can see that there are certain clusters of noise complaints. So for example, down here, you can see that there's less noise complaints over here. It's scattered over here in Brooklyn and Queens. And then in Manhattan, there are more noise complaints over here. So you can see that there are different patterns here, and they're a little more scattered in some places. And if you highlight, you can actually see, let's go for one of these. Let's see. If you highlight it, you'll see the neighborhood name, you'll see the Puma number here, you'll see the borough, you'll see the mean noise complaints, you'll see the high and low that was generated by the model because it gives you the probability distribution. And then you ask the question whether it may fit in or may not. And then you'll see like the median right here, median right there. Yep. Okay. So the final thing we're going to do is we're going to compare our testing model 2 to how does it predict with 2025. This vertical line right here basically shows you the ideal case. If the predicted, and so the X represents the predicted, and then the Y represents the mean. And so if the model predicted perfectly, then everything would pretty much be aligned along this vertical line. So if it's above the line, then the model is just basically under predicting the actual noise complaints. If the model, if it's below the line, then basically the model is over predicting. And as you can see, as the noise complaints increase, the model is basically over predicting. And the little numbers here are just basically the samples for the individual noise complaints. But so you will see that here. And so there's work that needs to be done. And so this right here to the right is basically a table that basically shows you, do the data actually match the actual how the model's predicting for that percentiles? As for example, you have right here, you have the 50 percentile, and does the data cover within the 50%? And it should match with 50, but right now you see it's 19%. And if you go up to the 95 percentile, it's only 0.48, which it should be a 95% if it's an ideal case. And so the model, we still have more work to be done with the model. And so one thing we could do is the first thing we could do is just map. I hope we can see this map right here. This is the map of New York City again. And so the height of the actual NTA, the boroughs, they basically indicate the error from predicting 2025. And then you have the color represents the average noise complaints. And just how we looked at the chart, the height, as there are more noise complaints, the lighter colors, they becomes more inaccurate. I said before, there needs to be work to be done to improve the model. And let's go back here. So what kind of improvements could we have? One improvement is that for likelihood, instead of using the Poisson distribution, we could use the negative binomial distribution. The reason is because the Poisson distribution takes into account only that the mean equals, the variance equals the mean. And so it's very restrictive, specifically for real world cases. With a negative binomial distribution, it's a little more flexible. It allows for variability, allows for real world data. And because the real world is messy, that's one of the things that we can do is give the model a little more flexibility and add the negative binomial distribution within the likelihood. The second thing we could do is, as we know, noise complaints may be influenced by other things. We only focus on the summer, but if we focus on other years, it could be the weather, it could be holidays, it could be special events, there could be more noise complaints, for example, on 4th of July. So we can incorporate other data sources into the model to improve and move closer to what is the actual mean of the noise complaints for those neighborhoods. So overall, how did Bayes help? So the first thing is that we have a transparent model structure, meaning that we're not just basically selecting specific, for example, learning type of method, we basically structure the model using probability distributions. Second thing is we capture the uncertainty of the real world. As we saw in the last chart, it didn't capture the high point, but that's just a matter of just improving the model, iterating improvement. And then we don't need a lot of data to basically create the model. We can start with a little data, and we could basically improve our prior and how we structure the priors, improve our likelihood to basically get closer to the actual mean of the model. And also, like I said, we can allow, for example, how we structure it in terms of neighborhoods, different neighborhoods to learn from each other. And so there may be some relationships between these two neighborhoods to basically just get closer to the true mean. And yeah, that's basically it.
Yeah, I'll let everyone unmute themselves at the moment. There were a few questions that did come in between that time frame. Gerardo asked, why are there missing neighborhoods?
So I just basically picked what the NTA has, what the NTA data has. So I wasn't aware whether they're missing data, what's the missing neighborhoods or not. So I think it's contained as within what NTA has. And I limited it to the top, middle, and lower neighborhoods. So I would say that if you look at the analysis and just run the notebooks, you should get more of the neighborhoods. Okay.
And Catherine sent a question. It's a bit long. Catherine, did you want to just unmute yourself and ask Moses? Sorry, not to put you on the spot.
No worries, no worries. I think in general, this has been a really interesting assessment of how to use statistical modeling to look at the data as exists. But I think that the framing of it has been like, this is where noise is in New York. And I think that what this data is showing is this is where 311 complaints are. And one of the things that we see when you bring, especially something that is easy to understand, like a data visualization, like a map to a policymaker, then they're like, oh, that's where I need to put resources, and that's what I need to solve. Whereas this doesn't really show you what the complaints are about, why people are influencing, or you're making the calls. And is it because maybe it's just they really know 311 really well, or maybe it's a certain population that has all the time to make phone calls. Could be anything. But I guess I'm not sure if you're part of the sort of cycle of then advocating to the city for what changes need to be made. But I wonder if you would speak to, or if you just want to say, this is how we should be interpreting this data. There's also been like Noel on here has also said like some interesting things about what are other data sets that we could overlay this with to give a little bit more understanding of the implications, whether it's the population, gentrification, income, other kinds of things that might give a bit more insight onto what it is that we're seeing. So thank you. And thank you for all of this. It's really cool.
Oh, thank you. Yeah, I didn't, to be honest, I looked at it from just doing Bayes analysis, and I didn't look at the policy perspective. But I think there's a lot of interesting questions. When I was preparing for the presentation, I was just like curious about exploring. And one area that really interests me, and I'm just speaking the one area that interests me is how wealth impacts noise complaints. Like our more wealthy neighborhoods complaining about neighborhoods and less wealthy neighborhoods. And that comes into, at the beginning when I started the presentation, it was very broad, obviously, in terms of like my thinking. And I was really excited about exploring these areas, but I had to limit it down. And so I think there's a lot of depth. And the funny thing is, I was considering moving to a place in New York. I was thinking, oh man, if I had a chart to show where the neighborhoods that have noisy and less noisy, then I would move to the neighborhood that's less noisy. There's a lot of ways to look at the data, but I was just really focused, I was just really focused on just presenting, understanding Bayes and how noise complaints can be used to conduct analysis. But obviously there's a lot of ways to look at it to develop some insights specifically for like creating policy.
Yeah, thank you for answering those questions. In the chat, Jacob also asked, can you say something about your choice of priors? He was also curious if you used neighborhood random effects. Based on the graph, it seems like it, but he's not sure if it was stated, or is the hierarchy borough, or is it the hierarchy borough to neighborhood?
So the priors. And the way PyMC works is that, I'm trying to remember, for the priors, you basically put in the distributions that you want, and then you define just to explain PyMC. PyMC is a library that I use as a Python library that I use for Bayesian analysis. And the way I define the priorities, I just basically put the distributions in, and then I basically define the data sources, which is the geographic data sources. And then I assign those geographic sources to those distributions, and it does what it does. And then the likelihood, I basically put in the real data that I define what the real data is, the complaints per day, and I aggregate that. And I just basically assign that to whatever likelihood I assign the distributions. So underneath that is, and I talk about black box. Underneath that, there's a lot of math that goes on that I'm unfamiliar with, but that's how it's pretty much structured.
Yeah, Jacob, he just wanted to confirm they're like empirical priors.
Empirical. I don't think so.
Okay. The next question was by Trang, and so they were wondering if you had the chance to consider or compare noise levels measured using ground-based sensors or other measurement methods, and whether these align with or correlate with your findings.
I would love to do that. I guess it's just if I knew about, first of all, if I knew about the sensors and noise data, I would do that, but also it's a limited time. But I personally would love to do that. If I had my own time, I would do that. If I had more time to do that.
Yeah, as of right now, these were all the questions within the chat. If anyone has any additional questions for Moses, please feel free to unmute.
Are you still based in Denver? Are you going to come out to New York?
Oh, I'm going to come out to New York on Saturday and Sunday. Actually, this is a random thing, but I actually work as like a digital nomad. And so I've been living in Medellin, Colombia for the past 3 years. But I'm going to be out in New York on Saturday for school data. Cool.
Oh, Noel also asked, how are noise complaints in Medellin?
It depends on where you live, actually. I live in a pretty quiet neighborhood. But one thing I noticed, is that if you live in an apartment that's closer inside, not the street, then obviously you don't hear all the noise. But if you live closer to the main roads, obviously you hear the more noise. I don't know about noise complaints. I don't know anything about the 311 data exists in Medellin, but I can say from my personal experience, that's how it is.
Yeah, Sherry's raising her hand. Feel free to unmute.
Sorry about turning my video on. Not ready for this visual, but I just out of curiosity, when someone asks the question, I find sometimes that there might be underlying assumptions made when people talk about wealthy neighborhoods versus poor neighborhoods. So I filtered the data set that I assume you use as one of your sources, which is 311 service requests from 2020 to present. And I filtered it for loud party as the problem type, and also for the zip code, which I know may not be equivalent in terms of the population. But 10035, which is a neighborhood that's traditionally considered one of the poorest in New York City, had 13,088 complaints, noise complaints for that particular category. And 10013, which is considered one of the most wealthy neighborhoods in New York City, had 10,195 noise complaints for loud party music. So whether that disrupts or confirms anyone's perhaps biases about gentrified and wealthy neighborhoods and their complaints and the number of complaints they might file versus poorer neighborhoods, I don't know, but I thought that was interesting.
Another thing I would say is that there is another data source that you can geographically break down New York even more, but it's just a little too much for me to do analysis. And so I kept it. I can't remember the size, but you can break it down to different building to building. You can even go in that narrower.
Yeah.
I didn't break it down to that, but you can go
Okay.
in here rather.
And having an equivalent sample size as you tried to do with how you were using that is a fair way to do it too. So I don't know. Someone's asking in the chat about the population distribution, and I don't actually know the numbers of people who live in each of those districts, but easy enough to filter just doing simply accessing the data set directly.